All right, give you a little bit of guidelines for solving log equations before we actually jump in and do some examples. These are just some guidelines, but they'll help you out. If there's just one log, go ahead and isolate it. So if it's being multiplied by something, divide by it, or if there's something being added to it, then get rid of that. Then what you want to do is, if there's more than one log, maybe you got two logs on one side of the equation, you need to combine the logs with either the product or the quotient rule. So that's where that writing as a single logarithm comes in a bit handy. After you've done that, you have two situations in step 3 here. Either you have log of an expression, you'll have x plus 5 or something as your expression, and that's going to be equal to a number. So what you want to do is you want to rewrite that in exponential form. So it'd be your base of b, so your exponent of c equals whatever the expression is, and then you solve it from there. Or you'll have log of some expression equals log of some other expression. Because logs are 1 to 1, you can set the arguments equal to each other, or set the two expressions equal to each other, and then you solve them. The domain of the log is everything larger than 0, so all positives. So maybe if you want to find your restrictions, is set your argument greater than 0, and then you'll need to check your solutions against that. So let's say your restrictions are x has to be greater than 7, and you get an answer of 2. You would say that that's not a valid answer because it doesn't meet our requirements for our restriction. Alright, so let's go ahead and look at an example of a log equation. We'll look at 2 times log of x plus 5 equals 1. And the first thing I'm going to do is I'm just going to note my restriction. So the argument here is x plus 5. So logs don't like zeros or negatives, so we'll just set the argument greater than 0. And we'll solve that. So my answer has to be greater than negative 5. That's my restriction. Okay. Now, we want to isolate the log, so we're going to divide both sides by 2. And then we'll have log of x plus 5 equals a half. Okay. And then we don't usually write the base for just log, but it's understood that the base is 10. So it'll be 10 to the 1/2 power equals x plus 5. And that's just rewriting in exponential form. Okay. That's the same thing as square root of 10. And then we'll subtract 5 from both sides, and that's going to equal x. And then if we want to check to make sure this is a valid solution, we're going to see does it meet the restriction. So what I need to do is I need to do square root of 10 and then subtract 5 from it. And I get negative blah blah blah. And that is larger than negative 5, so we've met our restriction, so it's okay. That's a good solution. Alright, let's look at another example here. This time I have half of log base 2 of x plus 5 equals 3. And again, my log's not isolated just yet. And also I might want to make note of my restriction here. So the argument here is x plus 5. So logs don't like negatives and they don't like 0. So we need to set the argument greater than or equal to, or just greater than 0. So our answer has to be greater than negative 5. If it's not, then we say that answer doesn't work. So it might be a no solution. Okay, so to get rid of that 1/2, I need to multiply both sides by 2 so that the log is isolated. Okay, now this is the definition of log, or rewriting in exponential form. So the base is 2. And the exponent is 6, and that's equal to the argument of x plus 5. 2 to the 6 is 64, and then we'll subtract 5 from both sides, so 64 minus 5 is 59, and 59 is greater than negative 5, so this is a good solution. Alright, let's take a look at another one. Log of x minus 3 is equal to 2. So we need to set the argument of x minus 3. We need that to be greater than 0. So our restriction is x needs to be greater than 3. This time the log's already isolated, so we can go ahead and rewrite as an exponential right off the bat. Remember, regular log is base 10, so it is 10 and the exponent is 2 equals x minus 3. Okay, 10 squared is 100, and then I'm going to add 3 to both sides, so we get 103 is equal to x, and that's certainly larger than 3, so that is a good solution. All right, let's look at another one. Negative 2 ln x. Okay, natural log is a log. The argument is x, so the x needs to be greater than 0. The base of the natural log is e, and you have a button on your calculator. It's usually associated with the ln button. So we're going to rewrite it as an exponential. So the base is e, and the exponent is negative 2. Base e, exponent negative 2 equals x. And if you weren't certain, you could have plugged in e to the negative 2, and you would have gotten 0.1353, and that's certainly positive, so it's a good solution. All right, let's increase the difficulty just a touch for log equations. This time I have 2 logs, so we're going to want to condense them in a minute here. So what I'm going to do first over on the right is I'm going to note my restrictions. So x minus 1, the argument in the first log, needs to be greater than 0. So that gives me the restriction that x is greater than 1. And log of base 6 of x minus 2, the argument there is an x minus 2, and that has to be greater than 0. So that gives me the restriction that x has to be greater than 2. So we have to be bigger than 1 and bigger than 2. So bigger than 2 is more restrictive, and that's what we're gonna base we're gonna make our test on. Is it has to be larger than 2. All right, so we're going to condense the logs using the product rule. Comes log of 6 and then x minus 1 times x minus 2 equals 1. Okay, so we can't forget anything. Now we're going to FOIL this, and we'll have x squared minus 2x minus x. It'll be a minus 3x, and the minus 1 times minus 2 gives me a positive 2. It'll be log 6 x squared minus 3x plus 2, and that's going to equal 1. Now it's a log equals a number, so we can rewrite in exponential form, or another way of saying it is using the definition of log. 6 to the first is equal to the argument inside. 6 to the first is just plain old 6, so I'm going to subtract 6 from both sides. So that's why we have 0 on the left. X squared minus 3x minus 4, and how the minus 4 came about was 2 minus 6 is negative 4. And then we're going to factor. So a lot of times these will factor. Sometimes, maybe the My Math will give you kind of a yucky problem where you have to use quadratic formula, but try to factor them first. So this factors into x minus 4 times x plus 1. If x minus 4 is a factor, then 4 is a root. If x plus 1 is a factor, then negative 1 is a root. Okay, now we need to go back and check our restrictions. So we're going to check against x being greater than 2. So 4 is good, and negative 1's not. Negative 1's not greater than 2, so we're going to cross it out, and x equals 4 will be our good solution. Okay, picking up the level of difficulty just a touch. This one's not going to be as bad as it looks. So I got 2 logs again, and I'm going to want to crunch them down into 1. Because there's plus in between, that means we're going to use the product rule. But now the arguments are a little bit more complicated. The first one's x minus 3 divided by 2. Now, the numerator is x minus 3, that's the top. The denominator is 2. So if fraction's going to be positive when you have positive divided by positive or negative divided by negative, we're going for the positive divided by positive because the bottom is 2. So we just need the top to be positive, and that happens when x is greater than 3. Same argument for the other argument, and so we have the requirements that x is greater than 3 and x is greater than negative 2. The more restrictive of the two is x is greater than 3. So that's the one we're going to use. And then we're going to go ahead and combine our logs using the product rule. Okay, so multiply fractions, multiply straight across, and then we'll go ahead and FOIL upstairs, and then 14 in the denominator. Okay, so now it's log equals a number, so we're going to use either what I call the definition of log, or we're going to rewrite it into exponential form. Because this is regular log, that understood base is 10, the exponent is 0. 10 to the 0 equals x squared minus x minus 6 over 14. And then maybe we'll make a note that 10 to the 0 is 1. Okay, so we're going to multiply both sides by 14 to get rid of that fraction. And 10 to the 0 is 1, so 14 times 10 to the 0 is the same thing as 14 times 1, which is 14. And that's equal to x squared minus x minus 6. Then we'll subtract 14 from both sides. Negative 6 minus 14 is negative 20. And this one will factor into x minus 5 and x plus 4. So if x minus 5 is a root, if x minus 5 is a factor, x equals 5 is a root. If x plus 4 is a factor, then x equals negative 4 is a root. Okay. Our restriction was x is greater than 3, so x equals 5 is good. However, x equals negative 4 is not, so we're going to throw that one out. Alright, this is our first example where we have logs on both sides of the equation here. So if I have a log base b equals log base b of something, you're gonna set the arguments equal to each other, or the expressions equal to each other, because the log's 1 to 1. If you can get the bases the same, then you can kind of think of it as it cancels out, and then you're left with the arguments equal to each other. We're going to first note our restrictions. X needs to be greater than 0. X plus 2 needs to be greater than 0. So x needs to be greater than 0, or x needs to be greater than negative 2, or not or, but and. X is greater than 0 is the more restrictive of the two, and that's what we have to go with. Natural log of x plus natural log of x plus 2. We're going to use the product rule, and we're going to combine them into x times x plus 2 inside the natural log equals natural log of 8. And we'll go ahead and distribute that x. Okay. So we have equal bases on our natural logs. They're both base e. And since natural logs are a 1-to-1 function, this means the arguments, or the expressions, are equal to each other. So this means x squared plus 2x equals 8. So I don't like saying it, but it's kind of like the natural logs cancel out here. This is a quadratic, and we're going to set it equal to 0, and then we'll go ahead and factor it. And I'll get two solutions. X equals negative 4, or x is 2. Now we need to go back and check our restrictions. X had to be positive. Greater than 0 means it's positive, so that means we're not going to take the negative 4, but the 2 is okay. Okay, let's look at one where we might have to use the quotient rule. And let's see, we got a subtraction of two logs, and let's go ahead and note our restrictions. X needs to be greater than 0. And then x minus 2 needs to be greater than 0. So being greater than 2 is the more stringent requirement, so we're going to go with that. When I subtract logs of the same base, I can use the quotient rule. So it's going to be log of x over x minus 2 equals 3. Now that we have log equals a number, we can use the definition of log. That's what I like to call it, or we can rewrite in exponential form. So the base here is 5, the exponent is 3. So 5 to the third equals x over x minus 2. We can go ahead and fraction bust and multiply both sides by x minus 2. 5 cubed is 125, so if I distribute 125, I get 125x minus 250 equals x. So this is just a linear. We've been doing quadratics the last couple of times, so we're going to subtract 125x from both sides so that we can isolate the x. So negative 250 is going to equal to negative 124x. Okay, and then we'll go ahead and divide both sides by negative 124. And then we'll go ahead and reduce. And then if you want to write that as a mixed number so you could be double sure, 2 and 1 over 62 is in fact larger than 2.